All right, today we're going to crack open a classic coding problem. And you know, it looks pretty simple on the surface, but trust me, its solution is this masterclass in efficiency that honestly every programmer should have in their back pocket. So let's dive right in.
Okay, let me just ask you this straight up. You've got a list of numbers, right? And here's the kicker. It's already sorted. Now, how would you efficiently find two numbers in that list that add up to some target? That word sorted, that's the secret sauce. It changes the entire game, so keep that one in your head.
So the official name for this puzzle is LeetCode 167, also known as Two Sum II. And that little 2 at the end, it's not just for show. It's super important because it's the signal that our input array is sorted. And that, my friends, is the clue that lets us solve this thing in a really, really elegant way.
All right, let's lay out the rules of the game here. We get a sorted array of integers. Simple enough. Our task? Find two numbers that add up to a specific target. And what we need to give back isn't the numbers themselves, but their indices. And here's a little twist. They have to be one-based indices. You know, like how humans count, not the zero-based way that computers love. The best part? We're guaranteed that there's exactly one solution, so no need to worry about any curveball.
So that sorted property, how do we actually use it? How do we leverage it to our advantage? Well, this is where a beautiful, almost common sense technique comes into play. It's called the two-pointer solution. Let's check out how it works.
You know, the core idea is just so simple, it's brilliant. Instead of the brute force way, starting at the beginning and checking every single possible pair, which would take forever, we do something much smarter. We start at the ends. One pointer on the smallest number, one on the largest, and we just work our way in.
So check this out. Here's the setup. We're going to plant one pointer, we'll call it L for left, right at the start of the array. And then we'll plant another pointer, R for right, all the way at the other end. The whole strategy, the whole magic, is just about how we move these two pointers toward each other, kind of like a pincer.
Okay, now for the fun part, the logic. How do we decide which pointer to move and when? It's actually way simpler than you might think, and it all comes back to that one golden rule. The array is sorted.
Here's the deal. At every single step, we just add up the two numbers our pointers are pointing at. Now, three things can happen. 1, the sum is too small. If it's too small, what do we need? A bigger number, right? And because the array is sorted, we know exactly where to find one, to the right. So we just nudge our left pointer one step forward. 2, the sum is too big. We need to shrink it. So we do the opposite. We move our right pointer one step back to a smaller number. And 3, the best case scenario. The sum is a perfect match. And boom, we found our solution.
Okay, theory is cool and all, but let's make this super concrete. We're going to walk through a real example right now, step by step. Let's actually trace where these L and R pointers go.
All right, here's our test case. We've got the array 2, 7, 11, 15. In our target, the number 9. Our mission is to find the two numbers in there that sum up to 9.
Okay, step 1. Our left pointer, L, is on the 2. Our right pointer, R, is way over on the 15. So, what's 2 plus 15? 17. Now, is 17 bigger or smaller than our target of 9? Yeah, it's way too high. So, what's the rule? If the sum's too big, we need to make it smaller. We do that by sliding the right pointer one spot to the left. All right, next up, L is still hanging out at 2, but R has now moved to 11. So 2 plus 11, that's 13. Are we there yet? Nope, still too high. So we do the exact same thing again. We need a smaller sum so that right pointer takes another step to the left.
And there it is. L is still at 2. R has now landed on 7. What's 2 plus 7? It's 9. That's our target. We've got a match. See how those pointers just closed in and found the answer? Pretty cool, right?
But hold on, we're not quite done. Remember that little detail from the rules? The one about one-based indices? See, our L pointer is at index 0 and R is at index 1. So, to give the right answer, we just have to add 1 to each of those. That gives us 1, 2, and that's our final answer. Easy peasy.
Okay, so we know it works, it gets the right answer. But why is this method so famous? Why do people love it so much? Well, it all comes down to its incredible efficiency. We're talking both time and memory here, which is a huge deal.
Think about another way you might solve this, maybe with something like a hash map. Sure, that could work, but you'd have to build this whole new data structure in memory. With the two-pointer method, all you need to keep track of are two little numbers, the position of L and the position of R. That's it.
It uses a constant, teeny tiny amount of extra memory, no matter if the array has 10 numbers or 10 million.
And speed? Is it fast? You bet it is. In tech speak, we call this O of n time complexity. But really, that's just a fancy way of saying we only have to make one single pass through the array. The pointers just move towards each other and they never have to look back. It's incredibly fast and efficient.
But this right here is the real showstopper. O1 space complexity, constant space. It means that our solution uses pretty much no extra memory. And in a world where memory can be a huge bottleneck, having an algorithm that's this light, that's a massive, massive win. This is what makes the two-pointer trick so slick for this specific problem.
And you know what's great? The logic is so robust, it doesn't get tripped up by weird edge cases. Got a really short array? No problem. Got duplicate numbers? It handles it. Even those plateaus where you have the same number a few times in a row, the simple logic of is the sum too big or too small just works every time.
So, if you remember just one thing from all of this, let it be this. The second you see a coding problem that gives you a sorted array, and it's asking you to find a pair of numbers, a little alarm should go off in your head. And that alarm should be screaming, 2 pointers! It's such a powerful pattern to have in your problem-solving toolkit.
So yeah, we've seen how amazing this is for a sorted array. But the core idea here, this concept of using pointers to squeeze in on an answer from opposite ends, it's way bigger than just this one problem. It's incredibly powerful. So I'm going to leave you with a little something to chew on. Where else, in what other kinds of problems, might this two-pointer technique be the absolute perfect tool for the job?